So the scientific approach to learning about matter is empirical, which means that it's based on observations and experiments, as opposed to like being philosophical or theoretical, where it's people thinking about stuff. So the scientific method is just a process for understanding nature. And it's not a neat set of rules, but there are some components to it. And so the key characteristic, those would include observation, formulating a hypothesis, experimenting, and then the formulation of laws and theories. And so this is kind of a weird little video about...
And now to something new and exciting in the AI space from Grammarly Go. It's a new product that offers...
I really should consider paying for YouTube so I don't have to listen to that. So this is just a little video without any words. So here's this guy. He's reading a book. And he's looking at the plants around him. And he notices that the one plant is a lot taller than the other plant. So this is an observation. And then he's like, why? What's going on? So he measures them. And that gives you data, stuff you can write down. So then he's going to come up with kind of an educated guess. What might have caused these plants to grow differently? And how could I test that? So his ideas are, one is that the plants got red too, and so he's going to do an experiment. Computers actually used to look like that. So measuring the plant. So here he's starting with two plants the same size, and he's going to read to one plant and not read to the other, and see if that makes a difference. And so he's going to do this for a long period of time, right? Kind of tedious, but science can be tedious. And measure the plants every day. Second hypothesis, music caused the plant to grow faster. So now we're going to play music for one plant and not for the other. And measure them every day, see what happens. So it's kind of like a science fair experiment, right? Yeah, we get the idea. Poor guitar. Test 3. Maybe it's because one's getting more light than the other one. So again, starting with the two identical plants, one is exposed to sunlight and one is not. Let's measure them every day and see what happens. Well, we kind of know what's going to happen here, right? Plants need light to grow. And so the plant that's getting more light is going to grow faster. But instead of just thinking about this, we're collecting data. We're collecting evidence that shows, yes, I exposed this to light, it grew faster. This one did not have as much light, it grew slower. So we get the results. Test 1, that wasn't right. Test 2, that wasn't right. Test 3, that's the difference. Now, is that the only difference between those two plants? Maybe not, but they determined that it did make a difference here. The end. to close that so it doesn't start playing again later in the lecture. That's always exciting. Okay, so anybody have any questions? The scientific method actually can be applied to a lot of different problems. Like your car's making this weird noise. Well, you can make observations. Does it happen when it's sitting still or when it's moving? You know, try to make observations about what's happening, and then you can come up with a hypothesis, right? And then you could test that. So maybe it's making this kind of weird clicking noise, and the faster you go, the faster the clicking happens. Well, maybe you've got a nail in your tire, and what you're hearing is that nail hitting the ground, and the faster you go, the faster it hits the ground. And so that can lead you to what the problem is. So observations in science are known as data. So they're going to be descriptions about the characteristics or behavior of nature. So this is an oil painting of a guy who lived a long time ago. Didn't they have great hairstyles then? Antoine Lavoisier. He lived in France. He was interested in burning things. Anybody out here like to burn things? I think all chemists are like secret pyromaniacs. I like to burn things, but I like to burn them safely. I don't like dangerous explosions, but burning things safely is just so fun. So he experimented by burning things inside of a closed container, and he weighed the stuff in the closed container before he burned it and after, and he made the observation that the mass didn't change when he burned the stuff. Now this is different than what happens when you burn something that's not in a container, right? If you think about a campfire, you have these big logs you stick on there, they're like really heavy, right? And then you burn them, and what's left? Pile of ashes, right? And you can just like scoop them up, they're really light, they'll float in the air, you blow them, right? Well, that's not the same mass as before, but when you do it in a closed container and you don't let anything escape, it weighed the same. So this was like, wow, what's going on here? So those observations lead to a hypothesis. His first hypothesis turned out to be really weird and wrong. But then it got better because he tested that one and that one wasn't right. But a hypothesis is a tentative interpretation or explanation, so kind of an educated guess. So one of his later hypotheses was that when a substance burns, it combines with something in the air. And because it's in a closed container, now we're not letting any of those things escape, and so the mass is the same. A good hypothesis has to be testable, right? We can't invoke a hypothesis that involves, invisible, undetectable aliens coming down and doing things, right? Because you can't test that. It has to be testable. And we test that using an experiment. Experiments need to be highly controlled. You need to think about all the different things that could affect this thing that you're looking at and try to control those things. That's why I like chemistry rather than like biology or medical research. You try to do research on humans. For one thing, there's only so many things you can do to them before they object, right? But then everybody's different and you can't control their activity level and what they're eating and their genetics. There's so many variables, things that could be different between the people. When you're dealing with chemicals, you can control those variables a lot more easily. And so it's more simple. So we get the results of the experiment. It may say, yeah, that hypothesis is right, or nope, that one's wrong. So in our little video, the first two were wrong. Is that failure? No. We learned something. This is not true. Okay? And then when it's not true, then sometimes we discard the hypothesis because we realize, yeah, that just wasn't a good one. And sometimes we take it and we modify it, we make it better and test it again. From those experiments, we can come up with scientific laws and theories. So a scientific law is something that just summarizes past observations and predicts future ones. So you've all heard of the law of gravity, right? So if I hold my keys out here and let go of them, what's going to happen? They're going to fall to the ground every time. Does the law of gravity explain why that happens? No, it just says this is going to happen, right? So that's a law. It doesn't explain. From Lavoisier's experiments, he came up with the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. That's actually a really big idea. These scientific laws have been established, multiple people have observed the same things, but they're still subject to being experimented on. And sometimes a law that we previously thought to be true is proven false because we've learned some new things, right? You cannot choose to violate a scientific law. You can't just say, I'm not going to obey the law of gravity today. You know, I'm not going to take the stairs, I'm going to just jump off the balcony here, and it's going to be fine, right? You can't. You're going to fall. Law of gravity. So the law describes how nature behaves. A theory is where we get into an explanation. So a theory is a model for why, for the way nature is, and explains not only what it does, but also why. And so later, John Dalton proposed his atomic theory, which explains the law of conservation of mass. The law of conservation doesn't do any explaining, atomic theory does. It says the law of conservation of mass is true because matter is composed of these little indestructible building blocks called atoms. And in a chemical reaction, what happens is we're just rearranging those little blocks. And so the mass before and the mass after, of course they're the same.
What did you say a theory was?
So a theory is trying to explain why something is. So, the law of gravity, being a law, just says what happens. So law says what, theory tries to explain why. And interestingly, the theory of the law of gravity is not fully understood yet. We know some of it, but nobody really completely understands gravity yet. But we'll leave that up to the physicists. So theories can also be validated or disproved by experiments. A thing that kind of sounds disturbing is we can never prove anything to be correct in science. I can't prove that something is true. I can only say that no one has been able to prove it false yet. And that's as good as it gets. Okay? So a well-established theory is as close to truth as we get in science. In everyday life, somebody says something, oh, well, that's just a theory. Well, maybe in everyday life, but in science, a theory is as close to fact as we can get. Okay. So it would be nice if the scientific method was just a series of steps and you do these things and you check them off and you get to the result at the end. Of course, it might be kind of boring too. The scientific process really involves going in a whole bunch of circles and failing a lot. So, you can start with observation and then you come up with a hypothesis about that and then you test it with an experiment. And maybe your hypothesis is right. The experiment shows that it is. And then you confirm that. So then we might end up with a law. If the experiment shows that our hypothesis is not correct, we may need to revise the hypothesis. And you can spend your entire scientific career going around in this circle. I know that doesn't sound too fun, does it? I'm not selling science very well. But those hypotheses, after they get tested a lot, can become a theory, and those, again, can be tested. So a scientist will do a study and an experiment and publish these results, and it's like, wow, this is cool stuff. So that's published in a journal. Other scientists read it and they're like, well, that sounds good, but I'm not sure. I'm going to try it and see if it works here, right? And so all the information is there in the procedure so that you could test it yourself, and other people will do that. And sometimes people have found out to have fraudulently published things because other people try to reproduce the results, and it's like, actually that doesn't work. Not good for your career, not good at all. But scientists end up proving themselves wrong a lot. Okay? And this is, well, I'm not going to go there. We're going to talk about COVID, but I'm not going to go there. Okay. So, in the lecture, there are some problems to solve and some questions to answer. So, try to answer this in your head. Which statement best explains the difference between a law and a theory? A law is truth, a theory is mere speculation. Or B, a law summarizes a series of related observations, a theory gives the underlying reasons for them. Or C, a theory describes what nature does, a law describes why nature does it. A, B, or C? C is really tempting because it sounds like a sentence that I said. It's B. Because C is exactly backwards. A theory explains why. A law says what happens. Okay?